right, time for another coding session. I'm pretty stoked with the improvements we got last time. The optimization to our assembly. It's it's kind of night and day in some places. Like this complex expression, this represents this guy here. Like when you think about it, there's like 1, 2, 3, 4, 5, 6, 7, 8 elements in there, I guess you could say, and there's like 1, 2, 3, 4, 5, 6, 7 lines of assembly. So not doing bad. In this particular case, you can see like we could use RSP in all these, but I'm not going to make that optimization because in some, like we're kind of lucky here in this case. Like all of our operands are just immediates, so we don't have to worry about it. But we also have, you know, like assignments 1 line, declarations 2 line. It's pretty awesome. The one thing that does take a lot of instructions now is this, which is kind of our general purpose copy, or it's like our memory address to memory address copy, I guess you could say. Yeah, so super stoked with that. Now what I want to do, we've got our arrays as well. But one thing that we did not get to was this. And that was kind of, when we went into our optimization of the generation, it was kind of, part of it was to allow for this kind of thing. Some of the changes will help with that. So now let's try and implement that. There's a few places where we can do array copies. We can do like an assignment / declaration. Yeah, we can do assignments and declarations. I guess we should test both of those. So if I say like array 3 and then array 3 equals array, and so then we'll try returning based on array 2 and based on array 3. And then the next thing is to pass a whole array as a parameter instead of just passing one of the elements. And then the third thing is to return an array, which I think is going to be the most complex. So I think we're just going to tackle those one by one so we can get kind of some small wins along the way. The first one, we've just kind of, I feel like we've just artificially limited ourselves. Where are we? We're in type check declaration. So I think it's type check variable is where we do it. Yeah, so here we have this check here, which basically enforces that we have, that we index into an array. We can't just use a whole array. So if we're going to change that, so currently what we do, because we make sure we're only using 1, we also set the length of our data type to 1, because when you index into an array, what you end up with is a single element. So that's why we set the length of the data type to 1 here. I think what we want to do instead is take away this check and then put an else here and say that the length is 1 here. So maybe we'll just assign the variable data type to our node. Yeah, we'll assign the variable data type to our node. And this -1 means that we did not index into it. So yeah, this is the variable. So in this case, we did index into an array. In this case, we did not index into an array. This is indexing into, this is not indexing into. So here, the data index would be 5, and here, because there's no indexing happening, it would be -1. So that's where we get to this situation. So if we didn't index, then we make the index 0 because it's just a single, yeah, because we don't need to offset at all. And here, if we did index into it, then we set the length to 1. So the data type is the same. So what we're saying here is, like, this has a data type of i32.8, but then when we do this assignment here, this thing will become i32.1, not i32.8. That's what this is doing. So we're no longer enforcing that it has to be length 1. So I think that might be all we need to do. Well, okay, so there is some more that we need to do actually, because we need to make sure that we're not, now that we can pass arrays around, we need to make sure that we don't try to use arrays in places that we can't use them. That'll make more sense when I show you the example places. So negate is one of the places I was thinking of. If we try to negate an array, it does make sense. We could negate every element of the array, and that's what I do want to do eventually. But right now, we're going to say you can't do that. Sorry. So I'm going to change this to our other kind of pattern that we normally have and say if not primary okay, then it's not okay. We need to declare that. And now we're going to have this check here where we say, you know, like, if the node's data type has a length greater than 1, that is, if we're dealing with an array, then we've failed to type check the primary. And the reason is invalid type. This node data value, this node dot value is not a type. We can get the type information from the data type, and this is something we already do here. So maybe I'll extract this out actually to a utility function, put it right at the bottom. So we'll say like data type name, oops, like this. So bring a data type in, and let's say if data type dot length equals 1, then that's easy. We just return the name. If it does not, then we return a string concatenation, which includes the name. Yes, so the first thing is the name, then an opening bracket. So I'm just going to print it so it looks like an array, you know? Makes sense, I think. So we need to have an element in here, which is going to be a number. So we need to convert the number to a string, and that's the length. So we need to declare this buffer, and we'll just make it an 8. a buffer of 8 bytes. And something is still horribly wrong. And it's because we don't have a return type. There we go. Okay, so I think this is going to be much better now. Where's our new check? So we go like that with the data type. And then also up here, when we say incompatible types, this is going to be quite handy as well, actually. We have that here, and I think one more place up here. Because now, so this is where we're coercing types and making sure that they are valid with each other. And they could be invalid if they, they could be both I32, but one could be an array of 10 of them, and the other one could just be a single I32, and that's not valid, which we should also put in here in our coerced types. Yeah, so when we're coercing types, we want to make sure that we only allow data types that have the same length. Yeah, because we could be coercing between like the type of this and the type of this. Like if I put I32 7, I would expect that to be an error because this is an I32 8. So we can't just assign between them. Or if it was just an I32 also, it should not work. Is that going to give me the right error? Yeah, so incompatible types. Sometimes it's just an empty string, and I kind of don't like that. Maybe let's tidy that up. So if data type dot name does not equal empty string. But we have a fixed size array. Damn it. So we append that to that dynamic arrays, and let's do the same up here. Could almost extract that out into its own function. That'll do for now though. There we go. Why is there a bracket at the, there's brackets on both sides. So I32 8 and I32 not valid. Also, like I say, if I put a 7 here, this should not be valid. But if I do this, this should be all good. I need to declare array2. Yeah, that's valid. So we've made that all good. Now in the generation, or maybe even in the type checking, I think the type checking should be fine. I think there's not really anything to do here. There's, it was right there anyway. So assignment, we're type checking a variable and type checking an expression. Yeah, we already did the type check variable stuff. So I think type checking we've all done. Now what we need to support is assignment and declaration, like I was saying. So let's go to declaration first. And I think the main thing here is that we want to make sure we allocate the correct amount of space, which should already be happening for declaration. Yeah, we times it by the length because we can already declare arrays, so that makes sense. And because our copy has just got this general purpose copy some set of bytes. Now I have to jump back. It means that this is actually correct, this assignment. So like this, you could think of this as the declaration and this is the assignment part of the declaration. And this copy is like totally fine. This has already got the right data size. So I think declaration's all good. Assignment, I have a feeling will have the wrong data size. Yeah, see, it's just using the data size of the data type. So I'm a stickler for consistency. So we need to use this data size. I think that's the only difference. If we're assigning a whole array, the data index should be 0. Because in the type checking, we clear that up, right? You have an index, so we put index 0, which means it's not going to affect this. I think that was an issue we had last time, right? And that's why we put this in here. And then we just copy it to here. Nice. Cool, cool, cool. So I think that should be it. Let's maybe have a look at the assembly. It's after the for loops, for one end. So here's allocating an array, assigning to part of the array, then copying from one element to another on the array. Now declaring a new array, which is 32 bytes. So then we go back 32 bytes and we go to the, so our source is 32 bytes back, which is this array. This array declared here. And then this is the space we just declared. And then we copy 32 bytes. Makes sense. Now, again, so we do a declare and it's just, that's right, yeah, it's just a declare. So there's no assignment. It's just allocating space. And then we assign to it. So that's the copy. And the sum is plus 64 because it's 2 arrays back now. Perfect. Yeah, I can't see an issue with that. And I think this here is doing the copy from the element of the array into a parameter. Oh, it's all these. So that's allocating the parameter, and this is copying the array element into it. So I think it all looks good. Let's test it. We should get 64. Boom. Yeah, I was quite confident about that one. And then if we try array 3, so that's the one that's testing that the assignment also worked. I mean, the assembly looked right, so 64. Cool. Yeah, so that one was not too bad. Now I think I'm going to get rid of these plus 2s. Do we still have those hard-coded? No, we got rid of the hard-coded procedures up here. And this was like our first procedures that we ever made, but they're kind of pointless. Are they ever used? I don't think they're even used anymore by anything. Let's get rid of this guy too. And just have a pow. So here, all these arrays have something in element 3. So let's go 4th element. And this should be able to have the same name as this, right? That should be fine. I wonder if that's, no, that should be fine. So actually that's I32, I32. I'll leave that call there, but we should be able to go like that. Right? So invalid token, this looks like the parsing failed at line 83, 34. So yeah, it's this token here. It doesn't like, it expected a comma. And I think that makes sense because we look at our grammar and it actually works. There we go. We can see in our procedure production, we've just put data type here, and data type just refers to the raw types. This type production refers to the potential to have an array syntax on the end. So we need to put in the procedure, we need to change these data types to type, like so. The return type we're going to leave as data type for now. But that means that in parsing, when we parse our procedure, here's the parameters. See, we're just allowing a data type node, but we actually need to parse a type here. And I think parse type, yeah, it takes in the node, the stream in the node. We might need to take the address. There we go. So a type can have the square brackets on it. So that should be what we need to be able to parse it. Okay, now parsing works. I don't think we need to change type checking, do we? If we go to type checking procedure, all we're doing is type checking the scope. Really? I'm kind of surprised. I thought there would be some sort of type checking on the parameters. No, I guess at this point there's no checking to be done. They're just declaring something. Yeah, okay. And when we do the call, we do type check the expressions to make sure they match. Okay, I think that's all good. And generation, let's just make sure that when we generate our procedure, again, we want to make sure we're allocating the correct amount of space. And we're not. So we need data type dot length. We need to multiply it by the length. Don't know why there's two lines there. I think that's it. So here, yeah, when we generate a procedure, basically we're just setting up the scope to include these variables. And so they need to have the correct sizing. Let's just have a look at the call, make sure there's nothing we need to do there. Where is the call? I think I'm starting to get to the point where I should probably separate this stuff out. I've got, nearly 600 lines. It's getting to be a pretty big file. I think I might split things out pretty soon. So here we have these procedures. This is it. The data size of the procedure should be times the length, right? Yeah, I think that's it. When we generate an expression, can we... Oh, something I forgot in type checking. We did this for primary. We said, you can't do this with an array. But also when we come into here, if we get past this if, it means that we're doing a binary operation. And in that case also, let's just use the data type we've just grabbed, this one. In this case also, we can't use an array. The other one that I had thought of was, like these expressions. But I think because we're putting in the expected data type, we have a length of 1 that's already, like the type coercion will fail already. So I think that's covered. So why was I curious about this? I think it's because when we go to our call, and that's right, we're here, I just noticed that there's this generate expression which is going to return a location. And I was just thinking, is it possible that that could return an array now? Can an expression return an array? It should be able to, as long as we don't end up in this stuff here, because we only support scalars here. But if we come into an expression and we just go right into generate primary and we find an identifier which is an array, then we just return that array, right? So we can return an array. And the type of information will be of an array. So then we just copy that array to the top of the stack. That's how it works when we do, because we pass our parameters by the stack. Yeah, I think that should work. Let's try it. Four. So the fourth element should be 4. That's correct. And I just want to, so I'm glad that this did not have a name conflict, because it shouldn't. And just for my sanity, like to make sure that it was like not actually looking at this variable somehow. I mean, I'm pretty sure that's not possible the way I've coded it. But I just want to eliminate that ambiguity, I guess. Okay, awesome. So we can pass in an array. Now I want to return an array. Ooh. What about increment 4th element? And that's going to return this guy. So that's just going to be like that. And then return array. And then we should be able to just do that. Can we do that? I don't know if my syntax actually allows that. It's probably not going to allow that, but that's interesting. I don't know if we'll fix that right now, but that should be allowed, right? This returns an array, so I should be able to just straight up index it. I think that's going to give us a parse error. Yeah, invalid token on 79. So let's just do this. That should be parsed okay. But now we get this one. Yeah, on 53. Yep, you can't see that, probably it's behind me. But that's the correct one. So back in parsing, we just need to take this parse type and put it here, but now it's the parent node, which is already a pointer. No? Yeah. It's a bit slow. It's quite slow to register, you know, the static type checking. So let's update our grammar also. So that's just changing data type to type for the, for the return. There, so our return is a type now. Cool. So now when we do our type checking, I don't think there's anything more to do here. But generation, this is going to take a bit of doing. And the reason for that because we're in call right here. This is how we do our returns right now. Our calling convention is that the return value goes into register 8, but our array is not going to fit into register 8. So we need to change our calling convention. And I'm going to change it so that we put the return value also on the stack. So before we do our call, we're going to allocate some space on the stack. Let's just put a param prefix on a lot of this stuff to make it more explicit. And this can be the return data size. That should be the param data size. And what is this param count? That is not used. So yeah, the idea is that before we do a call, I just want to allocate some space so that the procedure has somewhere to put the return value. So the return data size should be the same thing, but now we're dealing with the node itself. Yep, so we allocate the proper amount of space. We do the call and then we clear the stack. So this kind of stuff I want to put up here actually. And so this is where things get a bit interesting. So I've allocated some stuff on the stack. Now we need to move it from, like, this is a known place that from within the procedure we can refer to this known place because we know where the return value goes on the stack relative to the procedure. That's really important. Everything within the procedure we need to know where it is relative to the procedure, because the procedure we only compile once, right? Let me give an example. So if we go into POW, see it's referring to RSP plus 20 because it knows that's where the parameter is. And it's always plus 20. It's like relative to this procedure, at this point in the procedure, it knows that it's plus 20. And so we need something like that for the return as well. So that's why we've put the space here. But then we also need to forward that to somewhere that's relevant to the rest of the program. Because this is just some temporary space that I've allocated, right? I'm clearing it here. And the way that I want to sort of do this, actually, while I'm at it, I did want to rename this to location and location type. And that memory. I feel like that's better. I think that's more closely aligned with the proper, like this terminology. I don't know if that's probably not right, but definitely by making this not memory, then I feel better about making this memory. And these three are definitely terminology that is used for assembly. Okay. Somehow I broke everything doing that. But that's all right. Let's go back to our call. So in our call, I'm also going to give a destination location. So in the context of an expression, this destination is where the caller of the expression wants the result to be placed. Okay? That's the idea. We're still going to have this register num because this is going to be kind of a hint that we use for interim positionings. Actually, for this particular procedure, I think it's not needed, but we're going to keep it for other procedures. So now we have this destination, and we're going to copy to that destination. Yeah, so we don't need that, and it's the return data size. And we're copying from memory now. We're copying from the top of the stack. Because the return value was the last thing we put on the stack before the call. So it's at the top of the stack. And then we copy that to wherever we wanted it to be. That's the idea. And then I'm going to return dest. In this case, it's kind of a little bit pointless that we have this, like this return is always just going to be the dest. But I've kind of got it there for consistency with other procedures. So let's move to, I think we just need to rename these. Register dest. Another thing I wanted to do, because potentially, you know, the source and the dest could potentially be the same. So I wanted to put in here a case that just checks, like, is the source and the destination the same? Because if it is, what are we doing here? You know? So if the source type equals the destination type, I'm a bit of a stickler like this. I'm going to put it this way around. So the type and the, what else is it? Value? Value and the offset is the other one. So if everything in them is the same, I wonder if there's probably some shorthand way of doing this where you can just like compare two structs. I wonder if that works, comparing structs. Operators. Comparison operators. Comparable. So what's comparable? Struct values are comparable if all their fields are comparable. So I guess it goes through and compares all the fields. Okay. So that's much more concise. That's what I wanted to say. If the destination is the same as the source, there's nothing we need to do here. Okay, so that's the call sorted. Maybe I'll go down here, see if there's anything else. Well, this is already source and dest. I am tempted to switch these around so that it's more aligned with assembly. In assembly, the destination, like in a sub, the destination was always on the left. So I'd kind of like that to be consistent, but let's not do that yet. Let's get this return value working. So we're going to I'm going to continue this pattern in these other places like here. In this case, we are going to keep the register number. Because this is like, this register number now is basically sort of saying, hey, if you need a register to use, this is one you can use. You know, for interim, it's for like kind of like temporary intermediate values in the expression. So we generate a call which does not need a register number anymore. There's no need for it. We generate a primary, so that's sort of looping around. I'm going to call that the primary destination. And we do need to move that to a register. And if we're doing a negation, we know that it's not an array because type checking took care of that. I was just thinking because this move to register is not going to work on an array. So we negate it and then we return it. Because we kind of, well, it's register num. But we don't know if it's the, yeah, we used the interim register in this case. So primary dest, let's call it register dest. We have to declare it. Okay. What else do we have here? Generate expression will need the dest. We haven't got to it yet, but it will need it. So let's go dest location. So we need to pass the dest into there. Yep. And into these. I'm going to use the term dest a lot more now. It's like the destination. So here we're saying move to a register. So this is always going to override this. This is not going to be used in these. So what is it? Oh, it gets used. Oh, result operand is. Okay, it's only used there. It's not used there because it wouldn't work there. Okay, this is actually a bit crazy. I think we're lucky that it worked. I'm tempted to cut that out. That's giving us a lot of trouble. So let's clear these up. These are left-hand side destinations. Result operand is only used like once. And result location. Okay, interesting, because we need to return that as well. We need to return. Yeah, which worked before because we overrode it. Yeah, okay, so this is kind of the default. Which I guess is dest. Final dest. Let's put all the dests together. Final dest. So here, for these ones, we overrode the final dest. And LHS, RHS, LHS operand, it's only used once. You know, I'm tempted just to, it's like not really saving much at all. So let's just do that. Okay, so here, final dest, I guess we need to operand final dest. So, and final dest is what we return. So here, final dest is still just the original, it's the destination we were given, so it's going to go straight there, which is nice. These ones need to go into a register. Well, not technically, but we should, because of the complexity of, you know what, actually, I think we should do that for this as well. So I'm going to say final dest is that yeah, I'm going to say we always put it in a register. We won't move it, like we won't copy to the same register again. Well, we just need to do it at one point, but we need to do it. Now, if this happens, then the thing is that when we return our general expression, we're not giving it back. We haven't put it where it asked us to put it. So I'm going to wrap this. We did the same thing in parsing, I think it was. Maybe I'll call it dest1. You know what? I think we can take that off there. And whenever you call it with the inner one, you need to specify the register number. I think I like that. So when you generate an expression, I feel like that doesn't need to return the location. And now that I say that, I feel like this one doesn't need to either. We know that it is going to use the destination. So this one, we generate an expression. Where does it? We need to give it a destination. Well, afterwards we copy it to the top of the stack. Yeah, so we just directly say, hey, put it on the top of the stack. Yeah. This one should be _1. Generate call. Because it doesn't return anything actually. So let's say dest. It'll put it in dest, so we can just return dest afterwards. All right, I like where this is going. These are also need to be this kind. Is that okay? Yeah. Okay, so here, and because we said that copying is a no-op if we're already using that location, I can just do a copy, right? From dest1 to dest. I think I need to specify a size, right? Yeah, so we can just do something like this. And if it happens to be that it's already in dest, then this will be an op. Cool. Okay, so let's take a step back. We did all this stuff so that generate call, when you will copy the return back to somewhere useful to caller. That's nice. Oh, we need to fix these things up now. But return is another piece of the puzzle. Let's just fix these up for now, but we will need to do something with this return. So generate expression. Well, at the moment, we're trying to move something into register 8, which is not right. Yeah, so where do we want it to go now? We want it to go, so this generate return is going to be within the context of the procedure, right? So I think what we're going to do is we're going to create a special variable that we can put our result in. And then down here, we want to put the result in this register, right? The DI register. Is that right? Can I just do that? We'll switch the order of these because I don't want, I mean, this could be just a copy. That's an immediate 60 to the AX register. But because this puts something in the AX register, and this expression could, if there's a division in there, then it will use the AX register and overwrite this. So we need to do this second. Yeah, so I said here we want to use some special variable. So here's our variable, sort of access code. And the name of our variable, it's going to have just a special, we're going to make a special one called return. I put square brackets around it so that there can't be name conflicts, because variables can't be named like this. They can only be alphanumeric and underscore. They can't have square brackets. So this is reserved for our return. You can't index when you're returning. Like the expression could have an index. You could be indexing within the expression, within this expression. But the thing you return to, there can be no indexing, so we don't need that. So we do that. But we need to actually make a location from it. So here we're saying, all right, when we return, we want you to put stuff, whatever the result of the expression is on the return, we want you to put it in this return variable. And remember earlier, when we were doing the call, we allocated this space at the top of the stack. That's going to be our special return space. So maybe I'll do this now while we're thinking about this. So up here, see, this is where we're allocating space for all the parameters. So we just need to do this once more. but instead of a parameter node, we're talking about just the node. And we give it the special name. So this is the size of the return data type. That's how much space we are using on the stack when we do the call. And so we say that's where our special return value is. And then when we come back to the return, that's where it's like, because we're within the procedure now, so we can grab the position of that return variable and we can put the result of our expression there. So it's kind of a two-step thing. We put it in this temporary space on the stack created during the call, and then later we copy from there to somewhere that the caller actually wants it to go. And we have to do it in two steps like that because the procedure can't know this random place that the callee wants it to go. It can only know some relative specific spot, which is why we put it on the stack there. But I think that kind of covers that. And this one's not too complicated. When we do our assignment, it looks like we just want to put it here. So we don't need that copy, we just do this. Yeah, the result of our expression goes to the variable, and this is probably very similar. Like so. Here we are doing a test. We're generating expressions, so we want that to end up in a register, it looks like, register 8. So why don't we just say expression dest is register 8 with that size. Then we put the result of our expression there, so we don't need this move anymore. And then that's what we do our test on. And this should be exactly the same. Really need to tidy up this procedure. I don't like it. I think it's partly just because the grammar is not nice. I want to tidy up the grammar, and at the same time, this should get tidied up. And we need to deal with this at some point. Here's some more tests. So this should be very similar. I think we can just have like a reusable expression destination. Oh, I think in this case we can just go like that. Don't need this move to register business. You can just go to the expression destination. What's wrong? Oh, nothing's wrong with that. I don't like how it takes so long. And then we just test the expression destination, right? I think that's it. And then up here, so we can have a call. In this case, the statement is the call, which means that it's not part of an assignment or a declaration, which means we're not doing anything with the return. So I think I'm just going to say like if dest dot value is not empty. I wonder, actually, let's have another look in here. What is this nil business? What is it exactly? Like, I kind of thought of it as a nil pointer, but zero values. Values declared without an explicit initial value are given the zero value. The zero value is 0 for numeric or rune types, false for Boolean, empty string for strings, nil for pointer type ID, and any types. The expression empty brackets can be used for all types to act as a zero type. This is not recommended, it is not clear. And if a type has a specific zero value shown above, please prefer that. So you can refer to them as, so if I can say, can I just say it's, oops, don't know why that opened. Nil, it's, can I, no, but can I do this? Cannot convert untyped value nil. So maybe it's back where we were with the comparison operators. Where are the operators? Comparison. Doesn't say anything about comparison, comparing to nil. Oh. For operand x of pointer type, the pointer in direction denotes t if x is an invalid address such as nil. Nil slices. So the zero value of a slice is nil. I kind of wish it was like that for structs as well, you know? Because I just want to say, like, if this was initialized as empty, which is basically what I'm saying, right? Up in the, where is it? Quite high. Here. I guess I'm kind of saying, like, I just want a nil, and it lets me do that. No, it doesn't. Okay. Yeah, that's what I want. I just want to say, hey, this, I'm not initializing this, and if it has not been initialized, then yeah. But it seems like I can't do that with comparisons. I think maybe that's something I would like to add to my language. I think that would be nice. So everything compiles now, but because I got sidetracked with what I was just talking about, I'm trying to think, did we do everything we wanted to do? I think we did. Like, everywhere we handled this new dest stuff for expressions. And I think we did everything we needed to do for the returns. Yeah. So I guess we should, well, this one was the return. Yeah, so this should return, should still be 4. Is that just going to work? No, it's a 0. Well, I guess it should be 5. Actually, it should be 5 because it should have incremented it. Okay. I guess we can get rid of this. We already tested that stuff. Okay, so that did not work. And we need to figure out why. Let's have a look at the assembly and see if we can see anything that stands out as not looking so great. So when we return, we're doing a copy. It's a 4-byte copy, which is not right. Sorry, I'm jumping around a bit here, and I don't even know where I was trying to jump to. Let's have a look at the source. Yeah. So array is an 8-byte, an 8-element array. So it should be 32 bytes, like the other ones were. So this should be a 32-byte copy, but it's only copying 4, so that could be the issue. And that makes me think, wait a minute. We did put type there, and we did parse it correctly, right? Yeah, that's it here. So we've parsed it correctly. It should have the correct information on it. And it's the generation of our procedure. That seems to have an issue. Maybe it's because when we go to the return, where's our return? Here it is. We're saying where it is. And the expression kind of takes care of the size, I guess. The expression node knows how big it is. Well, this is wrong, although we don't even use it in here, which feels kind of wrong. Well, we pass in the expression node, so it's probably getting it from there. We probably just put this here. So if you don't need it for the other one. And to be honest, we shouldn't really, I put an and there, that's not going to work. We shouldn't really need to times by the length, because here we would have to have a scalar. So what's the issue here? Well, this is the return, and the count is too small. So when we go in here, aha! Here it's okay because our type checking makes sure that it's a scalar. This is the positioning. Here we also know it's a scalar. Okay. This is the problem, I think. Because this is where we do the copy. I assume it's that copy. Undeclared identifier array 3. And the index was out of bounds. Index was out of bounds when it didn't even exist. I feel like we don't need that error. Type check. Yeah, I should really split these into separate files. I'm doing way too much scrolling. Index out of bounds. So it doesn't exist. So if nothing's gone wrong yet, then say that. Okay. Yeah, we don't need the other error. Okay. 0 still. So here's our POW, and here's the return. The return is still 4. Okay. It's still copying 4 bytes. Oh no, POW should Was I looking at power before? No, increment fourth element. This is the one. So this is, okay, so this is copying 32 bytes now. And this looks legit, you know, it's grabbing a memory address, adding one to it, and then putting it back in the memory address. And it's definitely part of this here. So I think this is legit. This looks pretty good. Let's just double check when we call this, what it looks like. Well, this immediately looks a bit funky. Why am I copying from the top of the stack to the top of the stack? And again. Allocate two 32-bit arrays. We copy into one of them, allocate even another one, that's the return, I guess. So I guess we're allocating this one, the parameter, and the return space. So we copy into one of them. Yeah, this doesn't look right. So this is putting the return, so this should go, this destination should be different. And then, why are there like two of these? So this is part of the call. This is directly after the call. Generate call. So we have this one. If there's somewhere to put it, then we copy it. Ah, these are run the wrong way. No, they're not. From the top of the stack to this destination. Oh, but this destination, shit. This destination location has changed now. So because this destination location is pointing to the top of the stack, because when we evaluate this expression, or when we evaluate this, it's a declaration actually. When we go to the declaration, maybe there's some ordering we can change here. But so this is it here. Well, so it's just one line. Not much we can do about that. But so we're saying put it on the top of the stack. We just allocated some space at the top of the stack. Please put it there. But when we go into generate expression, we'll go in here, we'll go in here, we'll go in here. So this is saying put it on the top of the stack, please. But now we're getting this context. We're adding parameters to it. So we're allocating more stuff on the stack. So this is the top of the stack. This is the top of the stack. But this destination is no longer the top of the stack because we've just allocated a bunch of stuff on the stack. So what we might have to do actually is like clear, this is what we can do. We can revert the stack. So this is correct now, and this is wrong. Oh, this is another issue actually. Let's call it the call stack size. No, sorry. Call stack size. And then we need to also add the return to that stack size. So that when we clear this, we're accounting for that as well. So now the destination should be correct, and this should be wrong. But if we go minus the call stack size, that should take us to where the top of the stack was before we did this, which is where we put our return value. And nothing else is interfered with. Even though we've kind of freed that memory, we haven't given anything else a chance to use that memory yet, so it should be okay to do this. He says with lots of confidence. 0. Does it at least look? It's still RSP. Come on, give me a break here. How is that 0? How is that 0? Call stack size is 64. So if I dive into that copy, we'll go into this copy here. The source has an offset of -64. That has an offset of 0. So then the operand, if I dive into operand, because we said it has to be greater than 0 for us to index. So let's flip these, because I don't like negating my conditions. We'll just say if it's 0, if there's no offset, then we just do that. Otherwise, let's put the offset in. Then we should get plus -64. Does that work? Apparently it does. 5. Is that the correct answer? Increment 4th element. The 4th element was a 4. We incremented it to 1. We returned 5. Sweet Jesus. Okay. Whew. I knew that was going to be a beast. But I'm super glad we got there. And I think our compiler, the generation is a bit better off for it. Still got about the same amount of efficiency. I still love to see that. Like, that's just so clean. Very nice. Yeah, I think everything looks really good. It is a bit strange to see plus -64. not going to lie. But it works. All right. That's a good place to stop. We've been going for a while now, but I think it was worth it. Yeah. So I think we've basically got, I think that's basically it. We've got arrays nailed. I think another nice thing, though, would be to get pointers going. So we can do something like this. And that should be all we have to do. Just put that little guy there. Oh, and then here, we would also put one. So a pointer to this gets passed in, and this is expecting a pointer. But array, the indexing should still be the same. I want auto dereferencing. But maybe I'll go into that. I shouldn't go into so much. We've done so much today already. But I think that might be the next thing. Let's have a go at pointers. Cool. All right. Thanks for stopping by. Yeah, give us a like if you feel like it. Whatevs. And I'll catch you in the next one. Ciao for now.